Welcome. We're talking more about determinants, and today we're talking about section 3.2, and expect a second video right after this one. That's section 3.3, and that will end our chapter 3 discussions. But in this section, we're talking about properties of determinants, and there's really a big abstract kind of theoretical side of this that I love to go into, but I'm going to just brush over it really fast today. Because we're a little tighter for time, and I kind of want to get to the things that are a little more practical. But here's the short of it. The short of it is that if we have a matrix A and we want to row reduce that matrix, and we get a new matrix B, if we know the determinant of A and we know what this row operation is, can we figure out what the determinant of B is? And the answer is yes. And the way we do that is not by thinking about this as a row reduction, but by thinking about this as a multiplication. And so recognize that this is some elementary matrix, or this was some elementary row operation, so this is the same as multiplying by an elementary matrix. And so since this operation is the same as multiplying by an elementary matrix, this determinant is just that determinant multiplied by the determinant of your elementary matrix. So whatever your elementary matrix is tells you what it is. This hinges on one of the big theorems that we have in determinants, and we'll talk about this later, but it's that if you have the determinant of two matrices, the determinant of A times B, that this is the determinant of A times the determinant of B, and that is that determinants work very nicely with multiplication in this way. Again, because of the abbreviated condition of our semester, I'm not going to just go into too much detail about why this is the case. It seems pretty reasonable that this would be the case, especially when you think about elementary matrices and things like that. But okay, so in short, we're going to think about our second matrix as our first matrix times an elementary matrix. So if A reduces to B, then A, the determinant of A times the determinant of elementary matrix gives us that determinant of B. And so this is the big idea in thinking about this. Well, okay, in this case, we actually only have three types of elementary matrices. We have the type of elementary matrix that switches rows, and this is what it looks like in a 2x2 case. In a 3x3, it's just a bigger version, or 4x4, it's a bigger version of this. We have a scale row, which is where you have your identity, and you've just replaced one of the ones with a k, and that scales that row by whatever that amount is. And finally, you have row replacement, and this is where you've taken k of row 2 and placed it into row 1. Wait, k of row 1 and added it to row 2. Sorry, I said that backwards. But if we look at these, we can find these determinants pretty easily. So this determinant, you'll notice, is 0 minus 1. So this determinant is negative 1. This determinant is k minus 0. So this determinant is k. And finally, this determinant is 1 minus 0. And so this determinant is 1. So what you can see when we start to row reduce like this, if we do a row operation, row replacement, then A is equal to B, then the determinant doesn't change. So as long as we do a row replacement like this, our determinant doesn't change. If we do a scale, then our determinant of A, then what we had to do is we had to multiply it by whatever that scale is to get the new determinant. So if you scaled some row by 2, then that means your second matrix has a determinant that's twice as big. Finally, if you did some sort of row replacement, switch rows operation, then you'd end up with negative the determinant that you started with. So what we can see is that these determinants behave in a nice and predictable fashion. One thing that I was going to do, exercise 3.4 that I'm going to skip, is I was going to find a determinant in the most painful way possible. And that is, I was going to start with that matrix. I was going to start with that matrix A, and then I was going to row reduce it all the way down until we got the identity. And then I was going to take all of your row replacements and replace them with elementary matrices, find the determinant of each elementary matrix, and then solve the equation. So you'd have the determinant of all the elementary matrices times determinant of A equals determinant of this, which is 1, and then do that algebra and find the determinant of A. And it would have been really unpleasant. So I was going to do a determinant in the worst way possible, but I thought, how about we skip that? And you can just trust me that you could, if you wanted, do a determinant by breaking the row reduction down into the elementary matrix, multiply all those elementary matrices together. There's no practical reason why we would ever want to do this. The only reason we want to do is a theoretical reason. But there's a big theoretical reason why we care about this. And here's the big theoretical reason. It is, if we start with the matrix A, say it's a 3 by 3 matrix, and we start to row reduce, we know there are really only two possibilities. One possibility is when you row reduce, you get the identity matrix. But a second possibility is that when we row reduce A, we don't get the identity matrix. We have some sort of free variables in here. So maybe we get something like this, where you have free variables. So option A, option number 1, you row reduce down, and you get something that has an identity. Option 2, you get something with free variables. Well, let's look at the final result. The final result has a determinant equal to 1. Whereas here, the final result has a determinant equal to 0. This determinant's easy to see why it's 1. It just ends up being all these multiplied by each other. And this one's easy. Just use this bottom row and you get 0 times everything. And so you get determinant equals 0. So here's the question. If we started with a determinant, could we figure out which one of these two cases we're in? So if we're in this first case, if we started with determinant A, could we figure out which case we're in? Well, what we know is that if A reduces to this matrix right here, then we have a bunch of E's, E in up to E1 times A is equal to this thing. And what we know is that each of these ENs, the determinant of them, we end up with either something like either 1 plus or minus 1 or K. So we end up with some number on each of these. But what's important is that none of these are 0. So what you see is that these elementary matrices that we had just a moment ago, you can't get zeros from them because it's either 1 if it's a row replacement, -1 if it's a switch rows, or a K if it's a scale a row. And that K isn't 0 because you wouldn't scale a row by 0. So that means none of these are 0. So what does that mean about A? That means A must be not, because we have to have a bunch of not 0 things times A is equal to 1. So whatever that means, A must be not 0. So this is an important result. So that means that if we start with something not 0, or if we end up with something whose determinant is 1, we started with something whose determinant is not 0. But now, let's flip that logic around the second way and recognize what happens if we ended up with something where we had a free variable in it. Then you would end up with not 0 times A equals 0. What's the only way to get 0? The only way to get 0 is for A to be 0 itself. So what we can see is that in this case, this one is 0. So this gives us a really good method for taking the determinant of the original matrix and knowing exactly which of these two cases we're going to be in. So let me summarize that for us just really briefly, and we'll see why that's important. Okay. So what that means is we have one of two cases. We have our determinant of A, and one of two things happens. Either the determinant of A is not 0, or the determinant of A is 0. If the determinant is not 0, then that means it reduces to 1, 0, 0, 0, 1, 0, 0, 0, 1, or a larger or smaller version depending on the size of your matrix. If it is 0, then that means it reduces to something with free variables. Okay, now this is great because this type of matrix, you'll remember, is what we call invertible. A matrix that reduces to this is an invertible matrix, and it has every other property that we talked about all semester. So this type of matrix, the columns are independent. It spans all of R3. It has solutions for every possible equation has a solution. The homogeneous equation has only the trivial solution. So this has all those properties that fall with invertible. We can tell if it's in that category just by looking at the determinant and seeing if the determinant is not 0. Or 0 looks really bad, doesn't it? Versus if it is 0, then we know we're in the second category, which the second category is the not invertible category. The non-invertible category means that we have free variables. It means that our rows are our columns are dependent on each other. It means it doesn't span all of our n. It means you have non-trivial solutions to the homogeneous equation. So all these things are the same as not invertible show up. And so we can tell these just by looking at whether the determinant is 0 or not. So this gives us a nice, quick, and easy way. And by the way, this is going to show up in just a week or two when we introduce one of the last really big ideas this semester called an eigenvalue. And what we really want is to find an eigenvalue, we really want to create non-invertible matrices. And so we're going to be using these determinants to figure that out for us. That's going to be a really big idea towards the end of this semester. Okay, so that brings us to our theorem. And our theorem is just that A is invertible if and only if the determinant is not 0. And so that means that we can have our list of things. So we have our list of A is invertible. It's that column where we had A through N or something, different items that all mean the same thing. Determinant not equal 0 is the same as being invertible. And so we can add that to our list. Okay, so let's see, what sort of problems can we solve now? Well, we can take the matrix like this one, and we can ask, is this invertible? Well, how do we do it? Well, how I would do it is I would just find the determinant and just say, is the determinant of that equal to 0? And once we know if it's equal to 0 or not, then we know whether it's invertible. So let's find the determinant. This would be a great time for you to go ahead and pause your button, take a little time and see that if you can do this determinant yourself. Hopefully you can, especially if you've worked on the previous homework assignment. You're probably right on top of it. But okay, what am I going to do? I'm going to do row 1, and that's going to be -1 times the determinant, -5, -3, 1, 4. Sorry, I'm going to go a little bit quick here because I presume that we've done a few of these by this point. Okay, and then we're going to go 2 times the determinant, 1, 2, -3, 4. And then that's a minus because we go plus, minus, plus, and then 0 times the determinant. And I don't even have to write this out, but I did it anyway. Okay, so that means this turns out to be -1 times, and now this determinant, here, let me get these results. This is, I write these down here, it helps me. -20 and -3. So it looks like -20 plus 3, so it looks like I get -1 times 17 minus 2 times, and now what is this one over here? It is 4 times, and then we've got a -6 here. So it looks like 4 plus 6, so it looks like I've got a 10. And so it looks like our result is -17 minus 20, -37. It actually doesn't matter what the number is. The number could be any number we want, but here's the important final result. Is this invertible or is it not invertible? Well, this is not 0. So the determinant of A determinative A was most decidedly not 0. It was 37, and I don't think there's any way you could get, even if I made an algebraic mistake, I don't think I could have made a mistake so bad that this answer would have ended up 0. Okay, so what does that mean? So that means this matrix is invertible. So there's our result. So we could figure out that it was invertible just by taking the determinant, and once you take the determinant, you have your answer right there. And you can see why this might be useful, especially if you have a matrix that's really easy to find a determinant, but really hard to find the inverse of. You can know whether the inverse exists or not before you start your problem. Okay. Let's start the second problem. And so my second problem is, are these three vectors independent? So are these three vectors independent? And now what I want to do is I want to translate independent into invertible language. So I'm going to ask you a question. If they're independent, what should that mean about these three vectors? Are they invertible? Does it reduce to the identity? What is the determinant going to equal if they're independent? Well, notice being independent is the same as having an inverse, so it's the same as being invertible, which is the same as reducing to that identity matrix 1, 0, 0, 1. So it's the same as the determinant of that not equaling 0. So what I'm going to do is I'm going to do the exact same thing. I'm going to take these three vectors, put them into a matrix, and determine what the determinant of that is. So there we go. Let's just pull those off. And so what I'm going to do is I'm just going to find the determinant of this matrix and say, is that determinant 0? If it's not 0, they're invertible and therefore independent. If it is 0, they're not invertible and therefore not independent. So all I got to do is find this determinant and then I'm good to go. Well, for this determinant, there are multiple ways you could do it. I'm going to choose row 2 to do my determinant. And again, I'm going to go a little bit quick through this. Hopefully, like I said, work ahead of me. Hopefully you're on top of these things. But I'm going to do 0 times, but I'm going to do 0 times the matrix, -3, 2, -2, 2. Again, I didn't have to write this down. 1 times the matrix, -1, 2, 3, and 2. And then finally 0 times the matrix, -1, -3, 3, and -2. And now I have to think, are they plus, minus, plus? Well, it's plus. Our grid, our checkerboard goes plus, minus, plus, minus, plus, minus, plus, minus, plus. So our checkerboard here is a minus, plus, minus checkerboard. So that means I'm going to subtract this first one, add the second one, and subtract the third one. This isn't too bad at all because notice this is 0 and this is 0 because we're multiplying by 0. So really all we end up with is the number 1 times this determinant, and that determinant is just -2 and 6. So it looks like that ends up being -8. So it looks to me like we end up with -8 for our determinant. And since our determinant is -8, what does that mean? Well, let's come and draw our conclusion. So our conclusion, that means the determinant was not 0. So that means our matrix is invertible. And what that means is that means that those columns are independent. So we can see that the solution is that the columns are independent. So now you see how we can answer all of the questions that we've had earlier in the semester about is it invertible, is it not invertible. You can answer all those questions. Well, one, you could row reduce, and you could see if after row reducing, so you could row reduce and see if after row reducing, do you get the identity or do you get something else? So that's one way to go through those problems. But a second way now is to find the determinant. If the determinant is 0 or not 0, then that answers your question as well, because the determinant equaling 0 is the same as row reducing to something with 3 variables. not 0, row reduces to something without 3 variables to the identity. Okay, let's look at this last problem. And let's look at this last problem and see how it's going to go. I have exercise 3.7. What I would encourage you to do here is pause this and just ask yourself, can you guess what the answers to these are going to be? I'm going to tell them to you, but can you guess what they are? And if you can, then that's a really good sign that these things are making sense to you. If you can't, don't feel bad about it, by the way. Yeah, so no big deal if you can't. But if you can, try to guess, see if you can guess what they are. Well, let's start. What is determinant of A transpose? Well, what does a transpose do? A transpose just takes our columns like A, B, C, and D, and then just switches everything. So it becomes instead of AC going down, AC now goes sideways, and then we'd have BD. So transpose just kind of flips everything over that y equals x line. It's like you have this diagonal line right here, and it just flips everything over that diagonal line. And what you can see if you think about it is if you do a determinant, you do a row and then another row, and if you used columns as first column instead of the first row, you can have the exact same calculations as you would here. So if you use columns instead of rows, we get the same results for our determinant, and so that means the determinant of A transpose is the determinant of A. You get the same answer whether you're dealing with the transpose or not. Okay. What about A inverse? Well, tell you what, let's jump down. One of these I already told you the answer to. I probably should have written this one first. Determinant of A times B is the determinant of A times the determinant of B, and that's kind of a big result. So if we have a determinant of A times B, it are those two put together. So what about the determinant of A inverse? Well, what I would do there is I would recognize that A times A inverse has to equal the identity. And then if I use the fact that these things multiply, let's use our fancy notation, and that means that A, determinant of A, times the determinant of A inverse equals the identity. But what is the determinant of the identity? The determinant of identity has to equal 1. So from this logic, what does that determinant of A inverse need to be? Well, if I divide by A, it is 1 over whatever the determinant of A was when we divide by it. Notice that A couldn't be 0 because if it was 0, then you wouldn't have an inverse, and this problem wouldn't make any sense. Okay, so what is the determinant of A inverse? It is 1 divided by the determinant of A. Okay. What about determinant of 3A? Well, that's interesting. We're assuming this is a 3 by 3. Oh, this is an n by n matrix. Let's think of it as a 3 by 3 matrix first. So if we had A, B, C, D, E, F, G, H, I, and we multiplied it by 3, what does that do? It actually multiplies everything by 3, doesn't it? 3A, 3B, 3C, 3D, 3E, 3F, 3G, 3H, and 3I. And so how is that going to treat the determinant? It's tempting to think that you multiply the determinant by 3, but actually you multiply by 3 for the first row, and then you're going to multiply by 3 the second time, and then you're going to multiply by 3 again. So in fact, you've multiplied by 3 every stage along the determinant process, so you've actually multiplied by 27. So you've actually multiplied by the same number of 3's as you have rows and columns. So this determinant, it isn't 3 times the determinant of A, it is 3 to the nth power times the determinant of A. So whatever your 3 is, for every size in your dimension, you mark those out. Okay. Determinant of A, B, A inverse. By the way, this is a famous thing here. This is a process that shows up a lot in higher level math, in some more abstract math. Those of you who end up taking abstract algebra will see this type of result quite frequently, and it's like I said, it's a real popular thing to do. So, and we will end up with a theorem by the end of the semester where we take a complicated matrix, turn it into a matrix that looks just like this, where the middle matrix is a diagonal. And so what we're going to see is that this has a really nice determinant. What is the determinant of 2? Well, let's write it. Let's write it as A, B, A inverse. Let's use the bars. Well, what we know is that determinants multiply out. So this is the determinant of A times the determinant of B times the determinant of A inverse. But earlier, we saw the determinant of A inverse is 1 over the determinant of A. So what does that mean? That means we get the determinant of B all by itself. So what's nice is that this A and this A inverse, they can't cancel multiplication-wise, because we know that multiplication isn't allowed to be commutative. But determinants are commutative, because determinants, multiplication, this is multiplication by constants. This is not multiplying matrices anymore. And so this inverse and this one do end up reducing each other out when we get to determinants. So this is just the determinant of B. And what's going to be really nice about this is that once we have our problem, once we'll learn how to make a complicated matrix into an A and then a diagonal matrix. So that's a matrix that only has numbers on the diagonals and has 0 everywhere else. And then an A inverse. A diagonal matrix is easy because its determinant is just multiplying those diagonals. So the determinant of that complicated matrix will be really simple once you do this transformation. Okay. Finally, the last two, if a determinant of A to the 4th equals 0, the only way for that to be the case is for the determinant of A equal to 0, because you would just be taking the determinant of A times the determinant of A times the determinant of A. And if you have a bunch of things multiplied together equal to 0, one of them has to equal 0 as well. And now this is the important one. Well, it's not the important one. It's a place where we get confused a lot. The determinant of A plus B is not, I'm going to write this in red, it is not the determinant of A plus the determinant of B. So determinants work really nice with multiplication. They don't work really nice with addition. So you can't make that same assumption. Okay, so these are some properties. I'm not going to test you on these properties or expect you to know them. I think the big thing that you should take away is determinant of A times B is determinant of A times the determinant of B. And once you know this, every other property is just a consequence of thinking about that problem in some other manner. So thank you very much, and I'll see you in the next video.